Hello, everyone. I'm Matthieu Roussey. I'm a new professor appointed at the University of Eastern Finland, and my field of research is experimental photonics. And especially, I will talk today on prospects on integrated optics and photonics devices. So the entire scope of my research is based on the question how to pass from large laboratory equipment to portable devices that we can use in the field for measurements, for instance, in water or in industrial chains. So when you think about all the solutions we have and that are known, they are in a box. But quite often in integrated optics, we have to think outside the box. So this is all about that I will discuss today. So I'm 42, I'm French, I'm married, and I have one son. I'm living in Joensuu since 2011, and I got my PhD in 2008 from the University of Franche-Comté in Besançon. After that, I moved as a postdoc at EPFL for 4 years in Neuchâtel in Switzerland. Then my journey at the University of Eastern Finland started as a postdoc, and then I was tenure track professor, associate professor, and now I'm full professor starting in integrated optics. So what is integrated optics? If you look at those pictures, you can see a comparison between electronics and optics or photonics. In the 40s, computers were about the size of a room. Nowadays, they are smaller than a coin, and they are called integrated electronic circuits, and they are on the size on the chip and can be all connected together in order to make very complex circuits. In optics, it's about the same. You have in the laboratory large equipment, typically lasers or lenses, any kind of components that you know, and you combine them together in order to realize some functions. In integrated optics, our job is to combine them and make them small so that they can fit into one single chip that you can connect, for instance, to an optical fiber, which is actually the link between the chips in optics. If you go a step further in integration, then you can arrive to these kind of devices that are extremely small, extremely compact, with a very high level of integration and performing very complex actions. But what is our goal? Our goal is to lower the consumption. So we need a lot of engineering for that. We need to have small devices, so then the footprint is reduced, and at the same time, the material cost for Earth are reduced. So we need precise fabrication and also material science to understand what happens and to realize very complex circuits. We need to make smart design in order to reach the response that we need in order to perform our functions in optical chips. We need smart fabrication techniques also in order to reach the very high level of control and precision in fabrication, but also to transfer those techniques to large-scale production, which is actually what is needed for industrial prospects. For that, there's two things that are needed: a good team with good skills and advanced facilities. I have all that at the University of Eastern Finland. So, how we do this? Actually, we have to start with design. And for this, we have designing tools, simulation softwares, many methods to our disposal, and we are using them all, first because we can and because we need them. Each method has particular, let's say, specifications or properties that can be used to design each particular small element that we need to combine together at the end. We need an extensive clean room facilities in order to fabricate and characterize our devices. For that, the University of Eastern Finland is extremely well equipped. We have 200 square meters of clean room with all the key equipment in order to perform very challenging devices. And those devices, you have some example that are passing at the bottom of the slides. This is what we have realized those past years, and those are only a few examples. So we are working at the nanoscale, which is very small. 1 nanometer, the ratio between 1 nanometer and the diameter of an orange is the same than the diameter of an orange to the diameter of the moon. So this is pretty small. I have three main topics on which I'm working and focusing my research. The first one is on-chip devices. So you have understood that my work is to make integrated optical circuits, and for that we have to work on what we call wafers that we will cut into small pieces, forming the chips. On one wafer, we can realize millions of chips. But our goal here mainly is to develop new platform, meaning that we can fabricate in an easier way and make an easier integration of plenty of components without losing on the performance of those components. So usually we need high confinement of the electromagnetic field, of the optical field, together with low loss and high performances. So within one chip, we can now integrate different materials and different structures at different sizes, different scales. So typically we are fabricating lenses that are on waveguides with millimeter scale resolution or millimeter scale size. We are fabricating gratings with micron feature size, or we are going to photonic crystals or nano waveguides with really nanometer resolution. And this is to fabricate modulators, amplifiers, and other building blocks which are required in integrated optics. But not only in integrated optics, also in bigger components for many applications, typically telecom, automotive, sensing, optical computing. And those application domains are, let's say, the favorite ones for this topic. Together with those chips, one can integrate the key technologies for the future. I mean artificial intelligence and machine learning and quantum computing. So those are fully compatible, mainly because we are working with low-loss devices. My second topic is a little bit more on the theory and let's say fundamental science. It is about dielectric surface waves. You may have heard already about surface plasmons. Those dielectric surface waves are electromagnetic waves living at the surface of what we call a multilayer, meaning different materials that are stacked together. Those materials are purely dielectric, meaning that they are low loss, they are transparent, and they are somewhat easy to deposit. So one can fabricate those multilayer and excite those surface waves that are extremely sensitive to what happens on the surrounding, meaning that they are ideal for quantum optics and optical sensors. The third topic is really, I would say, integration of well-known optical phenomenon or optical phenomena, in order to be used, let's say, rapidly in water and atmospheric sensing and in industry. So the idea is to use our different facilities and packaging facilities in order to fabricate portable sensors. So those are based on different optical mechanisms like interference, speckle, diffraction, but also scattering or fluorescence measurements, spectroscopy in general. One can do more or less whatever we want and integrate it in a chip or in a box that can be used further in the field. So this is an illustration of the overall goal of this research. Combining all our developed concepts in order to go to ultra efficient devices with 4 main targets. Point of care diagnosis that we can do now with a smartphone, but we have to do it accurately and in a reliable way. That's why we are still doing research on this. It's not only manufacturing. We need to make smart sensor for degenerative disease, especially the monitoring of those diseases and the early detection. Actually, those smart sensors would be based on machine learning. We need high-efficient telecom devices using new materials in order to reduce the rare earth element consumption, and also at new range of wavelengths for such application, of course, in order to have more space in terms of channels in waveguide transmission. Finally, a very important topic nowadays, because it's a global challenge actually, this is the detection of the micro and nanoplastics in water environment. Those particles are polluting our lakes, seas, rivers, and they are eaten by fishes and other animals, and at the end, they end up in our plates. Our duty is now to find a way to get rid of them, and this is a big challenge since there's, of course, since 70 years, continents of plastics that are floating on oceans. So this picture is a vision that we have published recently in Optics and Photonics News. The idea is to integrate into one device that can be powered by solar energy and transfer through remote connections to boats or drones or whatever information about pollutants in water. But beside research, we have to remember that innovation and commercialization is important. My field of research is extremely linked to innovation and engineering in general leading to innovation. So those are a few examples of product that could be commercialized within the few years. So typically spectroscopy with a smartphone or enhanced Raman spectroscopy using low-cost plates or easy fiber-to-chip coupler for rapid testing of on-chip devices. So this is how I will end my presentation. I would like to thank all the people that have helped me to do all the work so far and who have given me all the basis actually for this work and the future work to be done. And I would say that future is just matter of imagination. So it's up to us to define it. I will thank you for your attention.